But what we have here, so is we have like the letter A, B, C, D, E, F, right? We have those six, right? We have those six characters. And so in the program, we're going to only be dealing with one character at a time, right? Just to kind of test out the basics of seeking here, and how it's going to work with a non-binary file. But when we think of this in terms of the bytes, like an array, we know that, for example, the A would be at 0, right? And then the B would be at 1, and then 2, 3, 4, 5, right? For the first 6 letters on that first line. So indexes or bytes 0 to 5 for those 6 characters. But right, then we encounter line return, right, in between the F and the G. And so the F itself, we said, was at byte position 5. But the line returns, since this is being run on Windows, which is going to have 2 bytes for a line return. So that would mean that the line return itself, or at least the first line return, would be at 6 and 7. And so the G would then be at 8, right? And then 8, 9, 10, 11, and so forth. So again, we can think of each character as like an array index, just keeping in mind that the line returns themselves also are, because this is an ASCII text file, right? The line returns themselves are also part of the contents of the file. And again, it's 2 bytes and 2 different ASCII codes for a line return in Windows. So it just means that those kind of things are taking up space in the file as well. So the first line really then is those 6 letters, which there's 6 bytes for the letters A through F, and then the 2 bytes for the line return, which then means that the G here starts at 8, right? And then 8, 9, 10, 11, and then similar idea, since the J here is at 11, then that means the next line return is at 12 and 13, and then the K is at 14, and so on and so forth. So that's the structure here of the file. And so we can do seeks to even a file that's not in binary mode. Because either way, ultimately in the end, right, the data physically in memory is binary, right? Everything in the end is 1s and 0s either way. And so we'll use the seek functions here similar to how we were using them with files in binary mode, meaning that in particular we'll still need to think in terms of the individual byte numbers. It's just the line returns now are taking up space physically in the file as well. And we'll also see different ways that we can use the seek function too. Because in addition to iOS begin, or BEG for short, we also have what's called iOS cur and iOS end, meaning that you can also seek to somewhere relative to where you're currently at, or you can seek relative to the end of the file. So those are alternatives to begin. So when you use begin, it means you're seeking relative to the beginning of the file, which is why we said that when you use begin, it's kind of like an array almost, because 0 means the first byte, 4 means if it's integers, right, would mean the second byte, and so on and so forth. Or here with something like this where we're storing characters, or especially if we had all the characters on one line and we didn't have any line returns, then it would be almost exactly right like an array. 0 for the first, in this case, character, 1 for the second character, right, 2 for the third character, and so on and so forth, because you're seeking relative to the beginning of the file. But nonetheless, we do have the options of things like seeking relative to where we're currently at. So instead of relative to the beginning, seek to where you're currently at, or you can seek relative to the end of the file itself. So in particular, if we do things like seek, maybe seek G if we're doing a read operation, and then we put in 0, iOS end, well, that's going to take us to what we call sometimes the true end of the file. meaning past where the last entry is. Or if we do, for example, here, assuming we're storing just a bunch of characters, if we do something like seek -1 and then iOS end, then that takes us to the last character, right? Or if it was numbers that we were storing, then we could do seek -4 iOS end to get to the last integer number. So again, there's different options there in terms of how you seek. You can seek relative to the beginning, beginning of the file, end of the file, or even the current location of the file if you want to do that. And then you still want to have the right argument for the first argument. So if you're, if you're currently at byte 6, for example, and then you say that you want to seek one position back to byte 5, well, then you could do -1 and an iOS cur, right? Because that would mean go one position back, but relative to where you're currently at, right? As opposed to relative to the beginning of the file. Or again, if you use iOS end for the second argument in your seek function, then it just means that you're seeking relative to the end, right, of the end of the file. So assuming we're storing a bunch of characters, then we can do things like -1, for example, to get to the last character, or -2. The only difference in this case being is that the line returns would have to be factored in as well, depending on how far back we want to go. But that's the general idea. So we can use all of those regardless of whether the file is in binary mode or not, meaning the iOS begin or BEG, the iOS cur, or the iOS end, right? So those can be used really in either mode. But because in this case, the file itself is not being treated as a binary file, we're not going to be using the read function, but we're instead going to use a function called get to read one character at a time from the file. But we'll combine it with the seek functions, which we've already seen before. So we'll see in some cases things like seeking relative to the beginning of the file, or the current location of the file, or the end of the file. But that's what our file looks like here. So in this program, we don't do any writing to the file. So these values were already directly written into the file, but we are going to do some reading along with seeking into this file. But so we have A, B, C, D, E, F right on the first line, and then these 4 letters on the second line, and then these letters on the third line, and then those letters on the fourth line. Okay, so here at the beginning, we're opening the file, just in input mode really in this case. So name of the file is letters.txt and then iOS in. Here we didn't actually call open, we just directly specified everything here when we created the object, but we could have also created the object first and then called open, like we've done with several of the previous examples. And then again, there's just several tests here, kind of testing out some of these basic ideas. So at the beginning, we called tellg, and then we call this function get. So the get function is going to just read one character, right? One byte at a time from wherever we're currently at in the file. So this is, and we haven't, in the very beginning, we haven't seeked anywhere, but we're printing out the current position of the file with telg. We're reading in 1 byte, and then we're printing out letter. And then there's going to actually be several different tests here, again, of things like end and cur and beginning. But in the first block here, what we actually did, just again, kind of playing around with things, was we did things like -2 and then iOS begin. And so one thing that we'll see is that in general, the file position doesn't wrap around, for example. So, you know, if you do like a negative number with iOS begin, right, that's just going to really take you to the end of the file. So we actually end up at the end of the file here because of the way that we did this. So we ended this block here with the clear, and then we did a seek to byte position 5, once again relative to the beginning of the file, and then printed that out. So at the beginning here, we printed out the first thing in the file. This is before we did any seeking at all. Here, we really ended up seeking to the end of the file since we put a negative number and also put in begin. So at the end here, we needed to do the call to clear since we reached the end of the file, right? If we want to be able to seek elsewhere, we need to clear that first. And then here with this third block, we called seek G again, but with byte position number 5, right? And then iOS begin. And then the next one here, showing an example of cur. So this one comes right after this block, right? So we called seek G, and then the get, and then printed it out. And then we said seek G1 iOS cur, meaning wherever we're currently at, relative to that position, go 1 position over to the right. So in general, it is possible to have either a positive number, right, or a negative number with your begin, cur, and end. In practice, right, there shouldn't be a negative number, you know, with begin, and likewise with end, it should be either 0, really, if you want to get exactly to the true end of the file, or a negative number if you're wanting to go, you know, for example, where the last number is, or the second to last number, and so on and so forth, and you can use a negative number. But with cur in particular, since that's really saying relative to the current spot, which could be, it could be a large file, and you could be, you know, anywhere within that. So in general, especially with cur, we may have either a positive or a negative number, depending on if we want to go to the right or to the left within the file, relative to where we're currently at. So this is just saying, and we'll look at the output here together, but wherever we're currently at, go 1 position over to the right, and then telg would tell you the position at that time, and then read that letter, whatever it is, and then print it out. And again, there's several blocks here, so we'll come back and look at some of the rest of this, but just testing out some more examples with cur, and then towards the end, we test out some examples with the end flag there. But that's the idea. So just dealing with a file, in this case, that's not in ASCII text, or not in binary mode, but rather in just the default ASCII text mode, but just kind of looking at things like the cur and the end flags and how you might use those in somewhat of a similar way as how you use the begin flag, but we can use all 3 here. And so we'll go back and forth a little bit between looking at some of this code and looking at the output here. And so at the very beginning, so because a lot of these we kind of paired up, right, a call to the tell function along with printing out the actual data value itself. So we did the reading with the call to the get function, and then we printed it out. And so at the very beginning, you'll notice that we have 0 and A, because A, right, the first line of that file was the letters A through F, right? Those 6 letters were all in the same line horizontally, and then we had a line return after the F. So the first thing there is just the fact that we're in the beginning, we're at byte position 0, and then we have an A. And then the next thing there that we'll notice is it says -1, and then also A, right? So that's the second block of output from our second block here. But if, again, back in the code, that's because we got the 0A ultimately from the first block here. But then you'll notice the second block was the -1A. Well, this took us really to the end of the file. And so what you're seeing in effect is we got to the end of the file, and then nonetheless, though, when we hit this cout statement, we were seeing A again, right? And the idea is that, if we're actually at the end of the file, meaning the true end of the file, past the last character, then we're not actually going to read anything, right? Because of course, if we're at the actual true end of the file, then there's nothing to read, right? We're at the end. So what we're seeing is just the value that was already in the letter variable, right? So that's how we're getting the A again. So we didn't really actually read anything here because, again, if we've reached the end of the file, then there's nothing to actually read. So the cout here is just showing us what was already in the letter variable from whatever we did previously. So with the second block here, we're seeing the -1 since we're at the end, and then we're seeing the A again because we didn't actually read anything, because to actually read something, we would have to go somewhere that's not right at the end of the file. So that's what's happening with the second block here. And then we end this block by calling the clear function, because if we don't call the clear function, then we're not going to be doing anything else for the rest of the whole program. Because we know that as soon as we reach the end of the file, we got to clear that flag out if we want to be able to seek elsewhere and do additional read operations, for example. So we cleared it out here. And then the third block is where we said, and this one was saying iOS begin still, seek to byte number 5 relative to, right, the beginning of the file. And so let's look at that, because then here we did the same things. We called tellg and print that out. We read the actual letter with the call to this function get, and then we cout the letter, right? So let's look at the third block here. So the third block is just meaning after the -1A is 5F. Because we said seek to byte number 5. So we went there to that byte exactly, printed it out, and then read in what was there, which was the letter F, because we had all 6 of those letters horizontally on that same first line. And then let's go to the next block here, meaning the one that's after the 5F. Meaning this block here. And so now it's saying, relative to where we're currently at, go 1 position over. Now, we do have to think about what that means, though. Where are we currently at by the time we actually hit that seek G on line 28? Well, we got to think to what we did in the previous block. So the previous block, we started on line 23 by going to byte number 5, and then we printed that out. We did call the get function, which similar to the read function, not only reads the character, reads the letter, but also advances the file position by 1. So by the time this block ends, we would then be at byte position number 6. So by the time we get to here, we're currently at byte position number 6. So meaning iOS cur resolves to byte number 6. And then we're saying relative to that, relative to byte number 6, go 1 over to the right, meaning byte position 7 in this case. So here what's going to happen is it's going to print out 7, and then we're going to read whatever's at that byte position. Now, we know that the way that the file was structured was we had the first 6 letters going from 0 to 5. And then we said that you had the 2 things for the line return, right? Because you got the carriage, and Windows, we call it really line return CRLF, or carriage return line feed. So 2 different ASCII codes that together do a line return. And that's part of the file itself, right? I mean, that's part of the actual data in the file is the line return itself. So we're at byte position 7, which is still part of that line return, because the next letter doesn't actually start until 8, right? Byte position 8, which is where the G was. So that's fine, but it just means that in this block here, we're actually still within that line return, right? We're still within that line return. So we're going to see 7 here as our file position, and then, but what's going to actually be printed out here is just the line return itself, since that's what's actually stored at byte position 7 within the file. So if we go back, and that's why you'll notice here as part of the output, you have the number 7, but what's actually coming below it is a line return, right? Which is why there's a little bit extra space there also, because that's what's stored at byte position 7 is that line return character. So that, again, that gives us an idea of cur. It just means relative to where you're currently at. So if you say 1 and you combine that with cur, it means 1 byte over to the right. So the idea is that here, here we're currently at byte number 6 because of what we did in the previous block. We're at byte number 6, and so saying seek G1 means go 1 over to byte 7. So we end up at byte 7, which happens to be where the line return is, right? Or part of the line return. Which is fine. It just means that's what's going to be outputted. So we're at 7 there. And then the next block here is actually another, yet another seek relative to cur, but this time it's 0 in cur. And so let's look at what we're getting after the 7 then. Well, actually, notice what's happening is the next thing is we're getting 8 and then G, right, with the next block. And so that was the block. So we get 8G next, and that was the block where we use the cur with 0. But same idea as the previous block. Really the same idea. So we know from all our discussion up here that in particular, we have to think about the effect of the get function itself, right? Meaning, so the get function call is what's actually reading a byte, right? But we're using this instead of the read function since this file is not in binary mode, right? So read and write are really only designed for binary mode, but we're operating with the file in ASCII text mode in this case. So that's fine, but we're just calling the get function to actually read that letter. But that again advances the file position. So, when we do this seek here, we said that you started out, you were currently at position 6, and then we're saying 1 with cur, which would seek to byte position 7, and then we read in that character, which was part of the line return. But then the get function itself also advances the file position by 1 byte. So by the time we get down to here, right, now we're currently at byte position number 8 because of the previous block. So we're going to be at byte position 8, but we're also saying seek relative to that byte position, but then we're also saying 0 here as our offset. So really, again, the number here is always like an offset, right? So we're adding nothing to cur. We're basically just saying go there itself. So we're going to seek to byte 8 then, since that's where we already would be at with just iOS cur. And then print that out, and then get the letter that's there, and then print that out. And then because of the structure of our file, G, right, the capital G was the first letter on that second line. So in particular, right, we're ending up there, which is byte position 8, where the G is. Okay, so that's the next block here. Just using 0 with iOS cur. And then we get 8G, right? So that's how we're getting the 8G after the 7 in line return from the previous block. And then let's look at what comes next after that. And then the next one is saying seek G to iOS cur. So just some more examples here with cur, but similar idea. We know that here we're at byte position 8. We read the letter, which takes us to 9, right? So by the time this block ends, we're at byte position 9. So we're at byte position 9 by the time we hit this, this seek. But this one says 2, right? Positive 2 along with iOS cur. So relative, right? Relative to where we're currently at, which would be byte position 9, go 2 over to the right, which would mean byte position 11. So we're starting to see the general pattern here that in particular, we do have to always take into account the impact of the read operation itself, right? Whether we're using the read function call in binary mode or whether we're using something like get here in ASCII text mode, either way, that's always affecting the file position itself. So we know that we're going to be at byte position 9 here at the beginning of this block at the seek G, but since we're saying 2, that's acting as our offset. So since we're currently at 9, go 2 bytes over to the right, meaning to byte position 11, and then get the character that's there at that particular byte position. But in terms of the file, we know that 8, it was the G, 9, which is where we're at in the beginning of that block, is the H, and then 10 is the I, and then 11 is the J. So in the next block there, we get 11J. So that's how we're getting the the 11J there. Okay, so we're at byte 11 here. And then similar idea. Now we have an example here where we're saying minus 3. So iOS cur and -3. Now we know from the previous block, this took us to byte 11. We read the character that was there, which then would take us to byte 12. So we can keep going in the same manner. It's just along the way, we need to always think about where we're currently at as we go to the next block or as we transition to the next block. But so the whole idea is that we were at 9 after the seek, right? We go up 2 to 11. We then read the character itself that's at byte position 11, which takes us to byte position 12. And now we're saying relative to there, go 3 back, right? Go 3 bytes back. So we're at byte position 12. Relative to 12, we're going to go back 3, meaning we're going to go to byte 9, and then we're going to read the character that's at byte 9. So start out in the beginning at 12, do the seek here, takes us to byte 9, read the letter at byte 9, which then after that's done takes us up to byte 10. And so let's look at the next output there. So after the 11J, the next thing that we're getting is the 9H, right? Because we're ending up at byte number 9 with going 3 back, right? So -3 means go 3 bytes to the left at this time. So negative numbers with cur mean go to the left, positive numbers mean go to the right. So go 3 to the left there, or go backwards 3 to where the H is, and then print that out. And then let's continue. And then now we're going to have some tests here with n, right? So we just did this block here, which we said in the comments that we're going to be at byte 10 when that ends. And then we have a seek to the end here. And you'll notice that we put in -1, and then we print that out. So the idea was that because of the way this file is structured, we know that we're storing a bunch of characters and along with some line returns. But the idea is that end itself, right, end with 0 would be the actual true end of the file. So kind of like an array, right? We know that size -1 is the last, the last where the last actual value is. So in this case, since we're working off of characters, end -1 is where the last character would be. So we're going to that last character in the file, because if we put 0, that would be the true end of the file, and that would actually trigger the end of file bit to be set to 1 and all that. But since we're saying -1, we're stopping short of the true end of the file, and we're going to where the last character in the file is. So iOS end, but relative to that -1, right? So instead of going to the end of the file itself, go one back from that. So rather than the end of the file, go to the last actual character in the file, and then we're going to be able to print that out. So seek to the last character, and then just go ahead and print that character out. So that's the goal of that statement. And so we'll see then in this case, that's exactly what we're doing then, right? So the last character was that O, and that's what we're printing out, right? So we get the 20, which is the byte position of that letter, and then we're printing out the O. And in the next block here, we're working off of end again, but this time we said -2, right? -2 and end, meaning second to last, right? Get the second to last character and then print that out. And again, we also are seeing here that since this block here didn't actually really reach the true end of the file, that we didn't have to, for example, call clear in between those two blocks. Although we showed an example of if you did another read up here after the initial read, right, then you'd have to call clear, because the whole idea is if you're seeking to one position before the true end of the file, the first get, right, is going to, read that character and advance the file position. But if you do another get after that, if you do another get when you're already at the end of the file, well, then that's going to reach the true end of the file and cause that end of flag bit to be set to 1. So, meaning if we had done like another get up here after this get, then you'd have to call clear. But since we didn't do that, and we weren't actually seeking to the true end of the file, but rather the last character in the file. So this block here by itself, right, does not cause us to reach the true end of the file. So we were still able to do the next seek here without having to do a clear in between. But if you seek to the actual end of the file, then, or otherwise get to the end of the file, then you are going to have to do a clear. So in general, right, there's different ways to reach the end of the file. One way would be to seek there directly, or doing things like seeking to the last character, reading the last character, and then doing another read statement, in this case, get function call, after you've already read the last character. So that would be another way to also reach the true end of the file, meaning where the EOF bit is going to be set to 1. But we didn't do that here in this case, so the next block is still okay, right? Just seek to the second to last character, and then go ahead and print it out, which is what we're wanting to do with that block. So here, that's what we're doing. So we're getting the N in particular at 19. And then we have a few more. So this one reads the second to last, and then we read it and then advance the file position. This one here, you'll notice, is saying seek to the end with 0, and then we're doing another get statement here. So let's look at that one first, because this time we actually put 0 itself as the position relative to iOS end. And so we've reached the end of the file at that point. Because keep in mind that we actually put in 0 itself. And but notice that we're getting the n again, right? Where n is actually the second to last character. But like we saw before, the idea is that if you're actually at the end of the file itself, right, then there's no read that actually happens, right? We have to be somewhere other than the end of the file to do an actual reading operation. So in this case, we're just seeing what was already previously in that letter variable. So which happened to be the n, right? The second to last character, because that was the last time that we seek to somewhere that wasn't the end of the file and did a read. So we're still seeing, we're still seeing the n there. And then the last block was doing another seek to end. But this time we put in the number 4, right? So 4 and then IOSN, but it's a similar idea for the most part. And again, that's not something that we would necessarily normally do, because we're effectively saying going 4 bytes over relative to the end, but the end, of course, is the end. So nonetheless, though, there's not going to be anything to actually read, right? Because we're still at the end of the file here. And so we just get the n there once again. And then one slight difference here is with when we put in 0, we're seeing the actual next byte position over, whereas when we put something like 4, we're seeing the -1, but really in either case, we've reached the end of the file. And then that's the end of the program. So just kind of showing the basic idea of how things like cur and end work along with begin. So we can use all 3. But we said that begin, when you use that it's in effect kind of like an array, because you're doing everything relative to the beginning. So 0 means the first byte, 1 means the second byte, so on and so forth. But as we saw here, cur means relative to where you're currently at, right? Relative to where you're currently at in the file, and then end meant relative to the very end of the file. Again, that was the last final blocks here. So again, just showing a little bit more. But the overall idea was that really, no matter what type of file we're working with, fundamentally, the seek functions work the same way. Meaning even with the ASCII text file, we still have to think in terms of the physical bytes, where each character, like the A, the B, the C, those are all 1 byte within the file. And then as we saw, the line return was really 2 bytes on Windows. But that just gives us some alternative ways to seek, right? In terms of seeking relative to the end of the file, or even seeking relative to where you're currently at. And then the other important detail with all of that was that things like the get statement, which is similar to read, but we're using it since it's not in binary mode. But both things like get, or put, which is something that you can also write to a non-binary file. If we want to, write a character, we could use put. But things like get, put, read, and write, those all affect the file position. So especially with things like cur in particular, which is always working off relative to where you're currently at, we have to take that into account. That's why we had to take that into account, especially with our calls to cur here, is we had to always take into account really, whenever the previous block ended, we had to take into account that the fact that the call to get was moving us up one position before we start the next block. But that's the general idea of how cur and end work. Yeah, the last read, -1 in general just means end of the file. So really with both of these, we've reached the end. But it's showing, for example, the 21 here when we put in the 0, which is the next byte actually in the file, the next byte over. Whereas here, it's actually showing -1. But really in both cases, we've reached the end of the file, which is why with that whole last, that whole final sequence, we were seeing n, right, with all the outputs, even though, right, n itself is really the second to last, meaning right, in terms of the order of the characters in the file. But the whole idea is that whenever you're going to the end of the file, there's not going to be a read that actually happens. So in terms of the output, you're just seeing what was already in the letter variable previously, which was the n, because that was the last actual value that was read in with the previous read operation. So that whole final block, we just keep seeing n over and over again. Because first, the first time we see it was when we seek to that second to last character, but the last 2 times are really at the end of the file, and so we're just seeing it 2 more times because we're not actually reading anything with those last 2 calls to get. So at the last 2 lines here, we're actually really at the end of the file. But nonetheless, you can see that if we put 0 exactly in terms of the value at least returned by telg, it's showing 21. But then if we put a bigger value like 4, well, then it's actually showing -1. And, so in this case, telg is doing a little bit of a different thing for both. But the main point is that really EOF is what we would check to actually detect the end of the file, rather than trying to detect it strictly through something like telg. Okay. If we aren't reading anything, then why isn't the variable? Because in this case, it's n, because when we did the last block here, meaning the real last block of actual reading, which was this block, that's seek to the second to last. And in this case, we actually were able to read. And so that is what was stored in the letter variable. But then, here it's seeing in effect, okay, well, wait a minute, we're already at the end of the file. There's nothing I can do, right? There's nothing to read if we're already at the end of the file. So nothing actually happens here, right? So the value that we see is just what was already there from whatever the last actual read operation was. So that's why we're seeing still n here. And for that matter, why we're also seeing n here again, because these last 2 blocks, nothing actually gets read because we've already, in both cases, we're already at the end of the file. So the value of the variable is just going to be whatever it was previously then, which, it could be a garbage value if we didn't read anything at all. But in this case, it would be whatever was coming from this block where we said -2 and iOS end. Yeah. So good. Yeah, good things to think about. But yes, that's why we're getting n 3 times back to back there, because we're really only reading the n once, and in the last 2 blocks, we're not really doing anything. Yeah. All right. Okay, so we'll look a little bit for a few minutes here at doubly linked list, and then we'll continue this some more on Wednesday. And then that'll be part of your extra credit assignment this week. We'll be working with some doubly linked list. And this came up a little bit with one of your previous discussion board posts, but the idea is that in general, we can have a linked list that can be traversable in both directions. So with a single linked list, we only can go in one direction with the list because each node has a pointer to the node to the right, or what we call sometimes the next node, but it does not have a pointer to the node that comes to the left or the previous node. And so we're able to do things like start at the head node and work our way towards the end by following those next pointers. But in particular, we're not able to go in the reverse direction and go backwards. So the general idea with a doubly linked list, and so you'll be revisiting some of the problems like insertion or deletion, which in many ways are similar, right, to how you might handle those with a single linked list. But the idea is that, we do have the pointers going in both directions, and we can take advantage of that. So it means that we, for example, can traverse the list from the end, right? For example, back towards the front. If we're doing something like maybe a search type algorithm, it means that we could potentially start at either end. So if we're doing a linear search where we're going to start at one end of the list and then keep going until either we visited each node and determined that the value that we're searching for is not in the list, or we stop as soon as we find it. Well, if we have the list as a doubly linked list, then we could potentially start at either end, right? And especially if the nodes were sorted, then you might even take into account the value that you're searching for, and that might determine which of the two ends, for example, of the list that you might start in with your search algorithm. So there are some benefits to having that kind of flexibility of being able to really go in both directions, as opposed to just being limited to only the one direction, as we are with a single linked list. So that's the major difference, right? So in the structure itself, in addition to that next pointer, you also have a pointer called prev, short for previous, which points at the previous node. And so the basic idea is that we need to maintain the head pointer, just like we did with a single linked list. We also should maintain a tail pointer, which some cases we might do that even with a single linked list, especially if we're maybe doing a lot of append operations or something like that. Then we might choose to have a tail pointer. But certainly with a double linked list, right, we definitely want to be maintaining a tail pointer to the last node. And then each node, right, has both a previous and a next pointer. So what you can do there is the first node's previous would point at null pointer, right? And then the last node's next would point at null pointer. So in terms of the structure, that's the basic idea, right, behind a doubly linked list is we have our different nodes here. Let's look at kind of a conceptual example here, and then we'll eventually look at the code. But again, each of those nodes is going to have both the previous and the next pointers. And then the last node's next, for example, is still going to be at null, right? That was the same as what we did with a single linked list, but also the first node's previous pointer likewise is also going to be at null. So that's how we can handle, dealing with that additional pointer there. So like before, each node still is going to have that next pointer. But now in addition to that, we're also going to have pointers in the opposite direction, right, for the previous direction. And then we'll have the head and tail pointers as well. And again, it's just kind of a generic example here, but we'll apply this to our student structure that we looked at. So that was the example that we looked at when we went through the all the single linked list operations, but now we'll look at it in terms of a doubly linked list. But that's the general idea in terms of the overall setup. So now each node has both next and previous pointers. So meaning we just have to have two different pointers in the structure declaration. So student star next, for example, student star previous. We can make the first node's previous point right at null pointer and the last node's next point at null pointer. And then the head pointer, as we know from our previous discussion, the head pointer itself is not part of the structure because there's only one head pointer. And likewise, the tail is not part of the structure because there's only the one tail pointer. But we maintain both, right? So the head either is pointing at null pointer if the list is empty, right? Or at the first node. And likewise, the tail pointer is either pointing at null pointer if the list is empty, or at the last node if the list is not empty. So we just maintain next and previous for all nodes, and then we maintain also the head and tail pointers. So we'll look at a little bit, and then you'll be doing more, right, as part of the extra credit, right? So you'll be revisiting some of those things like insertion, deletion, and so forth. But we'll look at a little bit of the idea here in terms of how to create, and it'll be a hard-coded example, but how to create a small list here that's a doubly linked list, and then how to do things also like, for example, traverse the list from the end to the beginning, right? Using things like the previous pointers and the tail pointer. But that's the basic idea here in terms of the overall setup, right? Just a little bit more that we have to maintain here. So it does, compared to a single linked list, right, of the same type, right? So for example, student as a single linked list versus student as a double linked list, right? It does take up a little bit more memory because each node now has to store two pointers, right? So each pointer, we know from previous discussions, a pointer takes up 4 bytes of memory to store a 32-bit address. So now each node has to store 2 of those rather than just 1. So a little bit more memory, but again, there's now a lot more flexibility in terms of how we might process the linked list nodes, because now we have a bidirectional structure in the sense of being able to go in both orders using the next and the previous pointers. So again, here in this diagram, we're seeing the general idea, and then we'll look at a short example of building a few nodes in a doubly linked list and then traversing it, and then you'll be doing some more advanced things with the extra credit assignment. Okay. So we'll look at that, and then we'll look a little bit at some of the basics also of object-oriented programming on Wednesday.